it's good to have at least some proofs in my mini course. So I will prove simplicity of A of G of this alternating full group, and give some ideas how to prove finite generation. But first, I need two lemmas, which are basic tools for multi-sections. So first of all, if you have a multi-section, remember it contains there are several disjoint Klopen subsets of the unit space, and then there are bisections between them which agree, so kind of form a commutative diagram. Now, suppose you take a subset, so let's call this bisection F. It consists of Fij, ij from 1 to d. And you take some subset U, so U, Klopen subset of, let's say, F11. Then you can restrict the multisection to the images of U in all the pieces. So apply this bisection, you get a piece here, apply the corresponding bisection. So apply all the bisections starting at F11. So you take F1i times U. In terms of groupoids, you can write it as times U. Actually, that's correct. There is no f of U. But more or less, it's just images. Let's call them Fii prime. So these are new components of a bisection, components of a new bisection. And then you say that Fij is the restriction of Fij to Fii prime. So that's a new bisection. So this new bisection, let's call it F restriction to U. It's the bisection, multisection Fij prime. So that's an initial definition of a restriction. Now, lemma 1, let U1, let's say UK, K in some set of indices, capital I, be a Klopen cover. Well, let's say finite covers. Let's take finite covers only. It doesn't matter. From 1 to M is a Klopen cover of, say, F11. And suppose that degree of F, so the number of components is at least 5. Then the alternating group corresponding to this big bisection is inside the group generated by the union of restrictions. So you take, let's now if you can see it, let me erase and write it. So you take the union, the group generated by the union of the alternating groups on the restrictions. So if you have a cover of a multisection by multisections found on smaller domains, then the group, the alternating group of the big multisection can be generated by the alternating groups of smaller multisections. Well, that's, of course, well, it's clear that it's enough to prove this for m equal to 2. So if you prove it for m equal to 2, you prove it for any m, just by induction. So we take the case when m is equal to 2. So we cover multisection by two multisections. So each component is a union of two Klopen sets. And so let's call this, you have U1 and U2. And we want to prove that the alternating group on the big multisection, it can be generated by the alternating group on one restriction and the alternating group on the other restriction. Well, that's an easy corollary of the fact that AN for n greater than 4 are perfect. So the commutator subgroup is the whole group. So let's split this the domain of the multisection in 3 pieces. So one piece is this different sets. The other piece is the intersection. And the third piece is the other difference. So if you have a permutation sigma in A, F, U1, it acts as sigma on piece number 1 and piece number 2. And trivially, so identically, on the, let's call them somehow. So all these ones is D1. The union of pieces number 2 is D2, and the union of pieces number 3 is D3. So it acts as sigma on D1 and D2, and acts trivially on D3. And a permutation sigma in FU2 acts as sigma in on D2 and D3, trivially on D1. So we have some alternating group AD, where D is the degree, and we have a map from AD to so there are 2 copies of AD, and there are 2 maps to the direct product of these ADs. One map maps sigma to sigma, sigma 1. The other maps sigma to 1, sigma, sigma. You look at the action of these 3 pieces. If you have a permutation in the alternating group, the first alternating group, it acts as that permutation on pieces number 1 and 2, trivially on 3. And if you take a permutation here, it acts as that permutation 2 and 3 and trivially on 1. But now if you take the commutator of, take one permutation sigma 1 in one group, another permutation sigma 2 in the other group, and look at the commutator. So let me recall you that this is sigma inverse, sigma 1 inverse, sigma 2 inverse, sigma 1, sigma 2, then it will act as commutator of these 2 coordinates is identity. Here you will get commutator of sigma 1 and sigma 2. And here you will get identity. So you will get a permutation that acts as the commutator on piece number 2, so on the intersection, and identically outside of the intersection. But AD is perfect, so this is any element of AD. And then using these elements, you get any element on the first coordinate. Using these elements, you can get any element on the third coordinate. So the range is that if you take the group generated by the range of this map, you will get the full direct product. You'll get all elements of this direct product in the range. So in particular, the diagonals, so all elements of the form sigma, 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 will be in the range. So it exactly means that AF belongs to the range. So AF is generated by these 2. So that's a very simple trick, which uses the only thing that it uses is the fact that the alternating groups are perfect. So, okay, that's lemma number 1. Another lemma is about composition of bisections, so or multisections in some way. Suppose you have 2 multisections. Now we have no restriction on the degree. It must be at least 3 so that you get non-trivial representation, non-trivial alternating group. So let's take this as a multisection F1, and then another multisection such that the domain of the other multisection is disjoint with the domain of this multisection, except for one component. So suppose you have another multisection which is disjoint, which is basically disjoint, but one component of this multisection intersects with one component of the other multisection. So let this be F2. Then, if you take the intersection of these 2 components, let's call it U, we can take the restriction of F1 to U and the restriction of F2 to U, and taken all together and taking all compositions, we will get a commutative diagram. So there is no problem. There will be no conflicts here. So it's clear that, so it's not a statement of the lemma. It's an obvious fact is that a restriction of F1 to U and restriction of F2 to U is a subset of a bigger multisection. Let's call it F. So you just take all images of U in one multisection, all images of U in the other multisection, take all these as components, and take all possible compositions. You get a bigger multisection. So let's call it F. So the statement of the lemma is that alternating group of F on F is inside the group generated by the union of the alternating groups of F1 and F2. That's also an easy statement. So I will not give all. So first thing that you notice is that if you take an element of F1, of a permutation inside F1, and take a permutation inside F2, and then take their commutator, the commutator will act non-trivially only on these pink pieces. So on these pieces, the commutator will act trivially. Because, so let me write it more carefully. So if you take permutation sigma 1 in A F1 and sigma 2 in A F2, then the commutator of these permutations will belong to A F. Because sigma 1 will act trivially on these pieces, and sigma 2 will act trivially on these pieces. So when you take commutator, the action on those pieces will disappear. So the only non-trivial action which will happen will be on these pink pieces. And now you have to show that these commutators that you will get will generate the whole alternating group. And that's a standard. For instance, you can show that cycles, all possible cycles of length 3 can be commutators like that, and you generate the whole alternating group. So in fact, the fact is that if you take, okay, just like such commutators will generate A of F. So that's some elementary fact about alternating groups. Okay, so we can, so why these two lemmas are useful? Here, this lemma allows you to compose by sections in some way, by getting some maybe smaller domains. But this lemma tells you that when you prove that something is, that when you have a covering by small domains, you can always take unions. So let me illustrate now this, show you how this can be used to prove simplicity, for example. Oops, I'm sorry. So simplicity of homomorphism groups, most of the proofs are based on more or less one idea. So let me give you a general statement. So let G, let me call it a theorem. Let G be a group of homomorphisms of a Hausdorff space without any other restrictions. Space X. For an open set U in X, denote by G bracket U the group of those elements G of G that G restricted to X minus U is identity. So that's what Nicolas Montauban called rigid stabilizers in his talk. Now let N in G be a non-trivial normal subgroup. Then there exists a non-empty open set U such that the commutator subgroup of the rigid stabilizer is in N. Moreover, of course, this is not a normal subgroup, so you can even take the normal closure of this. So something like this. So you get a bigger group. But the point is that if you know that your group has big rigid stabilizers, that gives you some strong restrictions on the on possible normal subgroups. The proof is very simple. I think implicitly this this theorem, maybe I shouldn't call it theorem, a lemma. This lemma is used almost in every proof of simplicity of homomorphism groups, but in different versions of the same lemma. Proof: let G in N be some non-trivial element. So I said that this is a group of homomorphisms, so I assume that the action is faithful. So it means that G, since it's non-trivial, acts non-trivial on some point, so there is a point such that the image of that point is different. So you have a point X, you have the image G of X. Now, it follows from Hausdorffness that you can find a neighborhood U of this point such that G of U and U are disjoint. So take any neighborhood and then take out the difference. I mean, take any neighborhood, take any two neighborhoods which are disjoint, and then take some intersection of that neighborhood and G inverse of that neighborhood. Okay, now take any two non-trivial elements, H1 and H2, are non-trivial, are any elements of the rigid stabilizer of this neighborhood U. Consider now, so let me draw the picture. So, sorry? Yeah, sorry. empty, yes. So H1 acts only here, only in U. So then if you take GH1 G inverse, it will act only here. Actually, let's take inverse of this. It's the same. H inverse acts only here, so if you conjugate, the conjugate will act only here. So now if you multiply this and this, you will get, so H1 times G times H1 inverse G inverse, it will act as H1 in this part, then some way here, and identically everywhere else. But note that this now belongs to N, belongs to the normal subgroup, because this is G is an element of the normal subgroup. This is a conjugate of that element. So this is in N, and this is in N. So this is in N. So you can find an element like this. Now take H2. H2 acts only here, and identically here, and identically everywhere else. Take now commutator of these two. It will act as only here, but the action which was here, because here it's identity, the commutator will be trivial. So it means that the commutator of H2 and H1 G, H1 inverse G inverse, it acts here on this part as H1, H2, and identically everywhere else. So it means that it is equal to H1, H2. But this is in N. Again, for the same reason as this is in N. You can write, we know that this is in N, and the commutator in the same way as here, it will be written as this element times a conjugate of the inverse of this element. So this is also, this is in the normal subgroup. So we see that the commutator of H1 and H2 is in the normal subgroup. But they were arbitrary elements of this registabilize. So it means that the derived subgroup is in the normal subgroup. So that's a very simple trick. Where? No, some group. Any group. So a subgroup, it is an arbitrary subgroup of the group of homeomorphisms. So for any subgroup, well, of course it may happen that this G, that for some open set it's trivial. So that will give you nothing, right? But if you know that they are non-trivial, then it gives you something. Right? But as you see, there are no conditions. The only thing that you need is that the space is Hausdorff. So you can get a vacuum statement here, but, but that's a completely general theorem. Okay, so now let's prove that A of a minimal groupoid of germs is simple. Let me remind you the theorem. Let G be a minimal groupoid of germs Then A of G is simple. So proof. Well, let N be a normal subgroup, non-trivial. Then, by the previous lemma theorem, then there exists an Klopen set U in the space of units, non-empty, such that if you take the derived subgroup of A of G acting on U, then this is inside N. Well, first of all, this group is, okay, so first of all, this group, A of AGU, is the same as A of G restricted to U. So you take bisections that live inside, I mean multisections that live just inside U, and take all alternating groups there. And this is perfect. So in fact, this is equal to this. So A restricted to U is in N. So this is your unit space. You know that there is some Clopen set such that if you take any multisection in this Clopen set, the alternating group on that multisection is in the normal subgroup. Now take an arbitrary multisection now of size 5 or more, of degree 5 or more. Take any point there and take the corresponding points in the elements. So the images of this point under the action of the elements of the multisection. Then this is a minimal groupoid. So there is a groupoid, an element of the groupoid which starts here, ends up in this open set. There is an element from there to here. There is an element from there to here, from there to here, and from there to here. You can find tiny neighborhoods of these points which are mapped to each other by the multisections, and such that if you map them by some bisections, here inside they are still disjoint. So if you take very, very small neighborhoods, they will be disjoint. Now, you can make these bisections, again, maybe shrinking the neighborhoods, into parts of cycles of length 3. And so on. So what we get together? So we have, we know that any permutation here belongs to the normal subgroup. So you take any even permutation here of these points inside, conjugate it by the union of these 3 cycles, you get a permutation of these, sorry, other way around. You take any even permutation of these points, of these pieces, conjugate them by the union of these 3 cycles, you get a permutation here inside. So any permutation, any even permutation of components, of small components, or small Clopen sets. So let's call this multisection F, of small Clopen sets around points of F, conjugated by the union of the 3 cycles, is an even permutation of Clopen subsets of U. Now that even permutation belongs to the latter belongs to A of G restricted to U. So what I'm saying that any sufficiently any even permutation of sufficiently small Klopen sets in the whole space can be conjugated to an even permutation inside U. And conjugated by a union of 3 cycles, so conjugated by an even permutation. So we see that for any any even permutation of sufficiently small Klopen sets belongs to N. Because, again, it's conjugate to something living inside U, and we know that everything living inside U belongs to N by that lemma. So any even permutation of small Klopen sets is in N, and then by lemma number 1, it means that any even permutation, and compactness, we get that any even permutation is in N. Then by lemma 1, A of G is in N. Any even permutation is in N, so everything is in N. So N is the whole group. So it shows that the group is simple. Yeah, it's Cantor set. Yeah, well, I said here the groupoid is groupoid on the Cantor set. The unit space is the Cantor set. Yeah, I didn't define A of G for arbitrary spaces, only for Cantor sets. Yes. Yeah, we are using that it's a Cantor set a lot. Yeah. Okay, so finite generation is, yeah. Sorry? Yeah, it wasn't used here. No, it wasn't. But it is used for proving finite generation. So I will not explain everything. I'll just give you a feeling how you do it. So in lemma 2, you get that if you take... Okay, let me tell you the idea. So the theorem says that if the groupoid is expansive, then the group is finitely generated. So expansive means that there is a collection of bisections such that if you compose these bisections, you get a basis of topology. So the idea is to put these bisections generating the topology inside multisections, and then use lemma 2 to produce multisections with arbitrarily small components. So roughly speaking, you know that if you take, so you have this generating set of bisections, and if you take sufficiently long product, assuming that this is symmetric, a sufficiently long product, you get sufficiently small neighborhoods of all elements of the groupoid. So that was definition of being expansive. So you could put these bisections, or maybe smaller bisections. If you have a set of bisections satisfying the definition, any set of smaller bisections, so any refinement, will also satisfy the conditions of the definition. So you find some, say, degree 5 multisections such that in these multisections you encounter all bisections from this generating set, or maybe of some refinement of this generating set. Then if you have such a bisection, actually if you have a bisection of length 3, then if you use the lemma, you take another bisection of degree 3, and then if you use the lemma, you will get a bigger bisection defined on a smaller component, so bisection kind of covered by images of this intersection, and containing the composition of these two bisections. In fact, this intersection is exactly the domain. You get shrinking because of you are composing okay, let me start over. So you have this multisection of degree 3, and this element of this multisection, suppose it is in the generating set, or suppose that it's a product of generators. And take another multisection of degree 3, such that this is one of the generators. Then when you're using lemma 2, you will get a bigger multisection containing the composition of these two bisections. So you get a product of generators composed with one more generator. So using lemma 2, you can produce new and new multisections such that elements of these multisections are longer and longer products of the generators. And this way you can get arbitrary small neighborhoods of all possible elements of the groupoid, and therefore you can get basically arbitrary multisections of degree 5 with sufficiently small neighborhoods, with arbitrarily small bisections. So then using lemma 1, you can produce any, say, multisection of degree 5. So that's the strategy of the proof. The main difficulty is that in lemma 1, you must be sure that all these 4 sets and this union are pairwise disjoint. So you must be sure that there is no conflict when you're doing this. You must have enough space so that you don't hit these components, that these components don't hit each other. So that's where you use the fact that there are 5 elements in each orbit, and that's an additional technical difficulty, but it's not very, very serious. So that's like the general plan, like strategy of proving it. It's really not very complicated. It's one-page proof, actually. So, okay, yeah. Yeah, in this lemma, this theorem G is a group of homomorphisms. Yeah, so you want to be sure that any non-trivial element moves some point. If it is not a groupoid of germs, you will have some elements of A of G, which acts trivially on the whole space. But there will be some isotropy groups which are not seen as non-trivial local homomorphisms. Okay, in the remaining 15, I guess, I started at 11:15. Yeah. Yeah, okay. In the remaining 15 minutes, I will start talking about some new examples of groups. Namely, groups, torsion groups and groups of intermediate growth constructed using minimal actions of the infinite dihedral group. And so maybe I'll just formulate the main results, and then tomorrow I'll give examples, and well, we'll see. So what is the infinity? The infinity is the group generated by 2 involutions, a free group generated by 2 involutions. An explicit description of it would be, for example, the set of all maps from X of the form X goes to -1 to power k x plus n, where k is 0 or 1, and n is an arbitrary integer. Or in other words, it's the group of all isometries of n, of z. So you can shift z, or you can flip over and shift. More algebraic definition is that it is the group generated by 2 elements such that by 2 involutions without any other conditions. Okay, so it is, this group contains Z as an index 2 subgroup. It's easy to construct, if you know many examples of minimal Z actions, it's easy to construct examples of minimal D infinity actions. So if you have a minimal D infinity action, then the action of Z inside, so as a subgroup, will be either minimal, or it will have, the space will be split into two Klopen sets, such that two invariant sets, such that Z action is minimal on each of these sets, and then kind of odd elements of the, so elements with minus will swap these two Klopen sets. But let me give you examples. So odometers, for instance, so minimal actions on the Cantor set. Odometers are, let me say, what is the binary odometer? Binary odometer is you take the ring of dyadic integers, so all infinite formal sums are ak over 2 to the k from 0. Sorry, no. ak times 2 to the k from 0 to infinity. And ak is either 0 or 1. So such formal series. And you can add these series, you can multiply them. And then the minimal action is it maps an integer x to exactly by this formula, to -1 to the k x plus n. So you have a binary integer, you can, plus adding 1 to a binary integer is the usual adding machine, the usual odometer action of Z. But now you also add the multiplication by -1, so the flip. Another class of examples are palindromic subshifts. So if you have a Z shift, so f in some finite alphabet to Z as Z shift, so it's called palindromic if in these sequences you will see arbitrarily long palindromes, so words that can be flipped. So if the shift is palindromic, then it's invariant under the flip. So if you have any infinite sequence, if you flip it, you will get again a sequence in this shift. So you can take the maps which take a sequence xn, n in Z, and transform it to the sequence x negative n. And you can take the sequence xn and map it to x1 minus n. And these two transformations of the palindromic shift will be of order 2, and they will give you a minimal action of the infinite dihedral group. So you're allowed to shift and to flip the sequences over. So if the shift is palindromic, then this gives you a minimal. If this is a minimal shift, then this will be a minimal action of the infinity. So there are many examples. Say it again. If the yes, that's the same. So if you have arbitrarily long palindromes, you can go to the limit. If the shift is minimal. If the shift is minimal and has arbitrarily long palindrome, for a minimal shift, being invariant under a flip and having arbitrarily long palindromes are equivalent conditions. Okay. Now, let me define the main construction. So, definition, let A be a homeomorphism of a Cantor space X such that it is an evolution. So A square is identity. A fragmentation of A is finite group A of homeomorphisms of X such that the following holds. First, for every G in A and for every point of the space X, G of X is A of X, or G of X is X. So every element of this group acts as A somewhere and as an identity somewhere else. And 2, for every X in X, there exists G in A such that G of X is A of X. So you don't lose anything. So basically what happens is the following. You have your Cantor space X. You split it into pieces, split it into some tiles, and these, so to say, closed pieces, and such that their intersection are fixed points of A. And then you define a group, you define elements of the group by saying, yeah, and these pieces are invariant. So you have piece P1, P2, P3, P4. Pi are closed A invariant. And any non-trivial intersection, any intersection is pointwise fixed by A. And then to specify an element of the fragmentation, you tell on which pieces that element must act as A, and on which pieces it must act as identity. And there are a finite number of these pieces. So in particular, all these groups will be, all these fragmentations will be abelian groups of exponent 2. So every element is of order 2, and every 2 elements commute. So this is similar to the notion of full group. So A will be sort of in the full group, but in the full group you require the set where the group element acts as another group element to be open. You want a clopen partition. Here you relax that, so it must be closed. So it belongs to a bigger, this A belongs to the bigger full group, the full group that was given in Lemaitre's talk, the group of all homeomorphisms preserving the orbits. So A will be in that bigger full group, but it won't be in the full topological group. Okay, so you can do it whenever A or B has a fixed point, you can fragment it in a non-trivial way. Namely, I need the following. Okay, let me formulate the theorem, and then I will tell you. Okay, the main theorem which I will talk about tomorrow, I will give examples of groups illustrating this theorem, and maybe I even prove it. It's not very difficult proof. Theorem. Let A and B be involutions, so be homeomorphisms of the Cantor set, of a Cantor set, such that A square and B square is identity, and the group generated by A and B acts minimally on X, on the Cantor set. Let psi in X be a fixed point of A, and let A and B be fragmentations of A and B such that the germ of every G in A at psi is different from the germ of A. So you take a fragmentation such that the germ around the fixed point of every element of the fragmentation is different from the germ of the element A. Then the group generated by A and B is torsion. Torsion means that every element has finite order. You get very general construction how to of building finitely generated. It's finitely generated because A and B are finite sets. Okay, torsion and infinite. So you get torsion, infinite, finitely generated group just by this kind of fragmentation. Let me tell you why, in fact, it's this strange condition is easy to achieve. If you have the fixed point, you can find 3 closed sets invariant under A. So namely, you take X minus the space minus that point. That will be some non-compact, totally disconnected space. And it's easy to see that you always can split it into 3 open A invariant sets. And then you can use the following fragmentation. You can take the element that X as A and A here, identity here, then moreover, you may always choose these 3 sets so that they accumulate on this point, and take A identity, and you can take identity AA. Well, for example, you can take a sequence of neighborhoods of this point such that they intersect, descending sequence of neighborhoods, intersecting at this point. You can make them A invariant. For instance, take these sets intersect with their images under A. So you get this strictly descending sequence of A invariant sets. Then take their differences in the neighbors, like assuming that they are Klopen, take their differences, so these rings, and then they say split the set of natural numbers into 3 non-empty sets, 3 infinite non-empty sets, and they say that this is the rings which correspond to one set, that's the rings corresponding to the other set, and that's the rings corresponding to the third set. So there's a lot of freedom of constructing these. Well, I will repeat this tomorrow. So you see that if you multiply any 2 homomorphisms, you get the third. So together with identity, this will give you a group, a finite group. It will be a fragmentation of A, and it satisfies this condition. Every element acts as identity somewhere where A doesn't act as identity. So the germs of all elements of this group are different from the germs of A. So this satisfies the conditions of the theorem. So the group generated by this and B will be finitely generated torsion. So will be an answer to a famous old problem, which was answered many times using different methods. But this method produces very small groups. So that's the only method. I mean, okay, I'll discuss this in more detail tomorrow. So what kind of examples you get here? For instance, they're all amenable. All these examples are amenable, which follows from Yushchenko-Monod theorem, together with a trick by Nicolas Mattebon. But some of them are of intermediate growth. So that's another thing which I want to discuss. And the condition that implies intermediate growth is purely dynamical. So there's some dynamical condition which implies that it will have intermediate growth. Okay, that's all for today. Sorry.